This is Daniel Gooseberry. In this video, I'm going to perform a one-sided test, a hypothesis test, to estimate mu in a context where I know what sigma is. So just as a warning, this entire video is going to contain one example of a hypothesis test. Hypothesis tests are very long, and there's a lot of steps to them. And I'm providing one-sided test in this context. I'll provide another two-sided test in this context. And what I would recommend is to go kind of flip through your textbook and Google some of these topics, like look for hypothesis testing for the mean on the internet, and look for as many examples as you can, because there's a lot of moving parts, a lot of things that can change, and it's worth just exposing yourself to a lot of examples and practicing a lot of examples to get this on. So I've just got one. This video is just going to have one example, and it'll be probably long anyway, so just a warning. So this is the context. We are estimating mu, so we don't know what mu is, but we do know what sigma is. And we've got central limit theorem results that'll help us. And we're going to take a random sample from a population. We're going to use X bar to test hypotheses about the mean mu, and we know the value of sigma. So we're going to have some central limit results that'll help us in this case. Like with confidence intervals, if we don't know sigma, we've got to use a slightly different method to do the hypothesis test. So let's go ahead and get started. As an example, not much is known about the new dog breed, the Kusawatchi Terrier. I just made that up. Does it sound realistic? We estimate that the mean adult weight of this dog breed to be 40 pounds. So we're estimating that the mean is 40 pounds. While the Kusawatchi residents don't know that the mean weight, they do know the standard deviation of the adult male dog weight is 12 pounds. So we have a standard deviation. We don't know what the population mean is. A random sample of 35 Kusawatchi Terriers has a mean weight of X bars equal to 37.4 pounds, and we're going to perform a one-sided test. So the null hypothesis is going to be what we think the mean weight is in this case. So we're gonna make our null hypothesis mu is equal to 40. Okay, so let's do mu is equal to 40 as our null hypothesis. Remember, the equal sign always goes in the null, and we're going to use basically anything but an equal sign in our alternative hypothesis. So we're doing a one-sided test, which means our alternative needs to have a greater than or a less than sign here. And while you may not know just kind of where this is going, if the mean really is 40, we've drawn a sample whose sample mean is less than 40. It's 37.9. So if we're doing a one-sided test, let's let our alternative hypothesis be less than 40, because this is less than 40. So in other words, based on this evidence, if H naught is not true, we're going to conclude mu is less than 40. So those are going to be our two hypotheses. The second component of a hypothesis test is the significance level, which the significance level means the same thing in this context as it does in confidence. When you make a confidence interval, the significance level is a way of saying the probability you're wrong. So here's a good definition. The significance level, which is denoted by alpha, is the probability that we reject H naught when H naught is actually true. Now we have another term for this. That term is type 1 error. So the chance that we reject H naught if H naught is actually true when it's actually true is called type 1 error, and we'll denote that by alpha, and we're also just going to call that the significance level. The probability this happens is the significance level. So all these ideas are related. So the chance that we reject H naught when it's actually true is called type 1 error. So like with confidence intervals, for instance, if we were doing a 95% confidence interval, we'd let our significance level be the opposite of 95%, which is 0.05%. And I like calling this the chance we're wrong. So we make a confidence interval for mu, and there's a chance that mu is not in there. There's a chance our confidence interval is wrong. There's actually a 5% chance it's wrong. So if we're 95% sure, there's a 5% chance we're wrong. In the same way, in this case, there's going to be a 5% chance we reject H naught when H naught is actually true. And then this is specific to this example. So we're going to let our significance level in this example be alpha equal 0.05. So this is common. There's a lot of common significance levels. Sometimes 0.10 is fine. Sometimes 0.01 is used. Sometimes 0.05 is used. You can let this be anything. But this is the chance I reject H naught and I'm wrong. So I want that to be around 5%. The next part of a hypothesis test is called the test statistic. And the idea of a test statistic is unique to each situation, and it's going to come from our central limit theorem results that we use to construct confidence intervals and we use to find probabilities. So in the context where we're estimating mu with sigma known, we know that X bar has a normal distribution with mean mu and standard deviation sigma over square root of n. So this comes from the central limit theorem. So this is true. So in this context, if our sample's big enough or our population is normal, this is true. And if that's the case, we can use the z-score formula, subtract the mean, divide by the standard deviation, and do this thing. This is confusing. We do the z-score thing. We take X bar, subtract the mean, divide by the standard deviation, which is this guy right here, and you get something that's normal 0, 1. So we can compute a number under the standard normal distribution by taking the mean, sample mean, subtracting our estimate for the population mean, dividing by sigma over the square root of the sample size. And we'll get something that's normally distributed. So in this context, where we're estimating mu with sigma known, this is our test statistic. So we're going to find this number. This is a number. So we're going to have to find this thing. And we're going to find it by plugging things in. And your book might use this notation for mu naught. So X bar minus mu naught. In this case, it's going to be 40 over sigma over n, square root of n, which are things. Okay, so let's go ahead and find this thing. You don't have to understand what this number means just yet. I'm going to show you later in this video what this means. Let's just find it. So it's a formula. I can plug in X bar. X bar is 37.4. Mu naught is what I think the mean is. So under my null hypothesis, mu is equal to 40. We'll call that mu naught. So 40 goes there. My standard deviation was 12. That's what the people of Kusawachi say the standard deviation is. And the square root of n was 35, so that'll go there. You find this number, you get negative 1.28. So this is my test statistic. So this is my test statistic. Try saying that 5 times fast. Note that this number follows the standard normal distribution. So because of the central limit theorem, this is going to fall under the standard normal bell curve, which is how we're going to talk about probabilities in this hypothesis test. But for right now, just be okay plugging things into the formula and getting this number and saying, that's the test statistic. Okay, so we have our hypotheses. We have our significance levels, 0.05. That's going to be the chance we're wrong. And we have our test statistic, which is the number negative 1.28 under the standard normal distribution. Now, this is where the rubber meets the road. We're ready to answer this question. If our null hypothesis is true, that is, let's make that straight. If mu is really 40 pounds, this is H naught. If this is true, we're assuming it's true. If this is really true, is it unusual if we draw a sample with a mean that's at least as small as 37.4 pounds? So the question is, if the population mean is really 40, like how strange is it that we get a sample mean that's like almost 3 pounds less than that? Is that unusual? It might not be. It might be fine. Like it might be common. It might be just as common to get that as it is to get a mean of 43 pounds. Like the sample size, the sample mean bounces around. Remember, the sample mean itself is a random variable. And if I'm dealing with a population, even if mu is 40, it's possible to get like one sample where X bar is maybe 41, another sample where X bar is equal to 39. Maybe. I'm saying it's possible. Anything's possible. The question is this a strange result? So if all this stuff is true, if the mean is really 40, which is my hypothesis, how unusual is it that I get x bar is equal to 37.4? It's possible to get it. I got it. But is it unusual is the question. If it's really unusual, then there's something wrong with our hypothesis here. If it's really strange, if the probability I get that is really small, there's something wrong with my hypothesis. That's the idea. So let's rephrase the question. So we computed a test statistic from this number that's under the standard normal distribution, and that's what the picture I have here. So let's ask the question in a different way. If mu is 40 pounds, if this is true, big if, hypothesis, is it unusual that our test statistic z is at least as small as negative 1.28? So asking, is it unusual that this mean is so small, is the same thing as asking, is it unusual that this number is as small as it is or smaller? So what I'm asking is, on my standard normal distribution, this is a normal 0, 1. Let me write that better. This is the normal 0, 1 curve. How likely is it on a normal distribution that I get the number negative 1.28 or something smaller than that? What's the probability that it happens? And is this an unusual thing? So remember the standard normal curve, like wherever the curve's higher, like things are more common. So it's pretty common to get stuff between 0 and 1. Like there's a lot of area there. It's not uncommon to get things there. But as you get closer to these tails where the curve is shorter, like it's pretty rare to get stuff out there. It's pretty rare to get stuff out here. The question is it strange to get this number, negative 1.28, or anything less than that? Is that strange? What's the probability there? Well, how do we do that? You guessed it, we're doing probability with the normal 0, 1 curve. So let's let normal CDF have its day, or you can use the table. But if you do normal CDF going from negative 9,99999 to, let's do 6 nines, to negative 1.28, that's your right endpoint, 0 and 1, you can find this area. And I have that on the next slide. I really want you to understand this question, because this is how we're going to draw our conclusion. So if we do that, I guess I didn't walk through it. Let's just do it on the calculator real quick. Let's do normal CDF, negative 999,999, all the way to negative 1.28. So I hope you see that that's the sliver right there. That blue sliver is what I'm typing in. 0 and 1. My answer is 0.100, round that up to 3. So that's my probability. It's 0.1003. My area is 0.1003. So that's like 10% of the distribution. Move the decimal, you get 10% of the distribution. Question again, is it unusual to get something in that range? Well, there's a 10% chance you do. Is it unusual? So we found that the probability that z is less than or equal to negative 1.28 is this number right here, which is greater than 0.05. Why does that matter? Well, because we're saying there's a 10% chance that you draw, you get a statistic that's that small. And we defined our cutoff for something being strange as something being 5% or less. So this is bigger than 5%. So we're going to say this is not unusual. We've done problems like this before. If something being unusual is 5% or less, 10% is not less than 5%. So because this p-value is bigger than alpha equals 0.05, we're going to call this not unusual. I may not have said this out loud. This is called a p-value, this whole probability. This is called a p-value, this area right here. That's the probability that z is less than or equal to the test statistic itself in this context. So we're going to say that if mu is equal to 40, the probability we take a sample that we get a sample with a mean at least as small as 37.4 is the same probability, this p-value. So this is the p-value. That is, we're going to reject H naught. If we reject H naught, we're going to have a 10.03% chance of being wrong. We don't want to do that because we only want to have a 5% chance of being wrong. So like there's really a 10% chance that we get this mean, we were only going to be upset if there was a 5% chance we got it or something less. So we're going to fail to reject H naught because our p-value is bigger than alpha. So this is a nice general statement worth writing down. And if it doesn't make sense, you can try watching this again and look at some more examples. But as a rule, if our p-value, which is this number, 0.1003, it's this area that we found. If our p-value is bigger than alpha, we're going to fail to reject H naught. And again, it's because we wanted to call something unusual if there was a 5% chance it happened or less. There's a 10% chance this happens, so it's not unusual. So we'll fail to reject H naught. We're perfectly fine saying that mu's 40. I'm not 100% sure that's true, but we can't say it's not true. So we're just going to hold on to it. So our conclusion is we do not have sufficient evidence to reject the hypothesis that the mean adult weight of male Kusawachi Terriers is 40 pounds. So that's kind of a nice way of stating our conclusion. This one uses statistical language and common language, which is helpful. It's a helpful sentence. Okay, so that's called the p-value method. There's another way to use the test statistic to get an answer. And so some people like using p-values. Some people like using the second method I'm going to show you. But just to recap, the second method, you would start out doing everything the same. So you start out with these hypotheses. Your significance level is just whatever it's picked out to be. And you go ahead and find the test statistic. So I found this number that's equal to negative 1.28 on the standard normal distribution. And now I'm going to do what's called the critical region method. The critical region method, it's asked the same question, like if mu is equal to 40, is it unusual if our test statistic is at least as small as that? But what the critical region does is it doesn't just throw this on the curve right away. Instead, it tries to find the number for which the area to the left is that lower 5%. Let me use a different color to demonstrate I'm doing something a little different. That the lower 5% is marked off by some number down here. So the critical region method uses what's called a critical value to mark off that lower 5%. So what number on this number line divides the lower 5% of the distribution from the upper 95%? And it ends up being this number right here. So this is called a critical value in this context. And this is how we find it. So this is a number on the number line in the standard normal distribution. So if we're looking for it in the calculator, numbers on the number line, we're going to use inverse norm. Inverse norm takes the area to the left, 0 and 1, because we're in standard normal. Whatever this number is, there it is, but just pretend you don't see it. Whatever this number is at this blue line, the area to the left is the lower 5%, this unusual 5% of the distribution. So my area to the left is 5%. That just so happens to be my alpha. So that's convenient. Doesn't always happen. It does in left tail tests. So that's nice. So if I do inverse norm in my calculator, you get negative 1.645, which is that value right here. So here's what I've done. I've divided my entire distribution so that anything that falls in this orange sliver is going to be rare. So if my test statistic is in here, it's going to have less than a 5% chance of happening, and we're going to call it unusual. Let me say that again. If my test statistic happens to be in this sliver, so something negative 1.645 or less, it's going to have less than a 5% chance of happening, and we'll call it unusual. I guess I'll just do this right here. Let's put the test statistic on the map now. So this blue line is negative 1.645. My test statistic ends up being to the right of that, negative 1.28. In other words, it's not in this lower 5%. So it's not unusual. Okay, so this is how the method works. If it's in the region, we'll call it strange, and we'll reject the null hypothesis. If it's not in the region, we'll say, it's not unusual. It's with this 95% over here. But if it's in the region, this lower 5%, we'll say, there's less than a 5% chance that happens. we'll call it unusual. So we marked off the critical regions such that if any Z value that falls in the region has a 5% chance or less of occurring. So since this is not in the region, the probability of its occurrence is greater than 0.05. We already saw earlier it was like 10%, but you don't have to do the p-value method and the critical value method at the same time. You can pick one. You don't have to do both. So we don't know exactly what the probability of its occurrence is. It's 10%, but we didn't calculate it. But we do know that it's bigger than 5% because all the things that are 5% or less are over here. This is over here, so it's bigger than 5%, which means it's not unusual. So we're going to conclude it's not unusual to get the statistic Z is equal to negative 1.28. That's not strange if the null hypothesis is true. So since it's not unusual, since it's not in the region equals not unusual. That's kind of a general thing to say. So not in the region, it means it's not unusual. Then we don't reject H naught because it's not unusual enough. Or we could say we don't reject H naught because Z is not in the critical region, that orange box. I know this, I'm throwing a lot at you, but this is a general way to conclude any, we could say really any hypothesis test. We do not reject H naught because Z is not in the critical region. If Z was in the critical region, we'd reject H naught. But since it's not, we won't. So here's the same conclusion I did with the p-value method. We don't have sufficient evidence to reject the hypothesis that the mean adult weight of the male Kusawachi Terrier is 40 pounds. Okay, so that's the end of my example. Like I said, this is one big hypothesis test problem. Now I'm going to make another video that does a two-sided test in the same context using Z's and the standard normal distribution. So make sure you watch this video. Of course you just did. And the other video for the two-sided test. And keep in mind that we did a left-tailed test. A right-tailed test is really similar and worth looking at some examples to figure that out. So watch that next video.